So
Yeah, great. I think we can get it started. I can give you an introduction. So, Professor Eugene Vinitsky is a assistant professor at NYU. He works on scaling up multi-agent reinforcement learning system for the design of capable and multi-agent autonomous system. During his PhD, he worked on designing algorithm and controlling for more than 100 autonomous vehicle traffic smoothing system, which was deployed in the field for a week and demonstrate the very efficient high level energy improvement. And UC Berkeley, he received his PhD in control engineering and received a master and bachelor's degree in physics from UC Barbara and Caltech. He spent time at Tesla, DeepMind, Facebook AI research, and was a researcher on the Apple Spatial Project before moving to New York City. Yeah, thank you so much, Eugene.
all right. Well, thank you for the nice introduction, and thank you all for having me. I'm not certain what time it is there, but it's a pleasure to be able to come talk to you. So yeah, I'm Eugene Vinitsky. I am in civil and urban engineering at NYU, and I'm affiliated with a bunch of other centers at NYU. Um, I wanted to start off this talk. And by the way, feel free to interrupt me with questions if you have them. I can't see the chat, so Diamo, if you can like chime in if somebody has a question.
So
Um, so
there is a Q&A tab. Feel free to either ask a question in the tab or you can raise your hand. I can allow you to talk.
Yeah, sounds good. So I wanted to start by talking about how I got into multi-agent RL. And the reason is it's kind of pertinent to why this talk is the way it is. And the way I got into it is we had this project at Berkeley that my advisor ran, and some other folks. And the goal there was to take 100 autonomous vehicles, semi-autonomous vehicles, and deploy them onto a highway to get rid of these like stop and go waves that you see here. They drive in a particular way such that you would eliminate the stop and go waves, and that would improve the energy efficiency of the highway on average. And we spent a lot of time on this project. And in particular, one thing we really wanted to do was to kind of do this as like kind of a large scale multi-agent simulator, right? So the cars would still be decentralized, but they would kind of implicitly cooperate in a way that would kind of improve performance. And it was just very hard. In comparison to single agent RL, I feel like a lot of the time there's a lot more kind of intricate components, a lot more tuning, a lot more sample complexity. And so it's less of this like black box that works in a little bit in comparison to single agent RL. I mean, that's not to say there aren't huge multi-agent successes. There have been, but it's a lot more intricate, I feel like. And you know, if we think about how single agent RL works, it's kind of one algorithm nowadays that, you know, this is PPO making your robot do great spinning tricks, you know, like all quadrupeds at this point are kind of PPO and RL based. You know, DeepSeek R1 kind of PPO RL based. It's like really starting to work. Like single agent RL is having its moment. And what I want to hopefully convince you of is that we're starting to see a similar thing happen in multi-agent RL. And I'm going to talk about two pieces that I hope that we've contributed to the story about how self-play RL is going to be like a very scalable toolbox that you can use to solve hard multi-agent RL problems. And if you like really scale it up, if you choose to go down this route of scaling, can be used to design extremely robust, almost human level, and I'll caveat that because there's some subtleties there, um, autonomous driving planners. So I'm gonna this talk will have two parts, and we'll go through it, and hopefully you'll see the connection. So we're going to start by talking about imperfect information games, and in particular, I'm going to talk about this paper we put on the archive about 2 weeks ago called "Reevaluating Policy Gradient Methods for Imperfect Information Games," and the authors are highlighted here. And I particularly want to highlight the first equal co-authors, Max, Nathan, and Saban. So some quick terminology, because I'm not certain, you know, we all come into this with different backgrounds and maybe some of us are less familiar with this. So we're going to be talking about multiplayer games. They're going to be n players. In this case, we're going to talk about two-player games, so 2 players. We're going to use I to index the ith player. We're going to use pi sub I as the policy of player I, or the controller, or you know, whatever terminology you use. R sub I is going to be the reward of player I. And we're going to be talking about zero-sum games, in particular 2-player zero-sum games. So we're going to have that R0 plus R1 is equals 0. So if one player wins, the other player loses. They're always in total opposition at any time. And we're mostly going to be talking about imperfect information games, or IIGs. These are games with hidden information. Like as an example, if you want to keep in your head, is like poker. Like poker is a canonical IIG, right? There's all sorts of hidden information about your partner's hand. Um, and these games are important for a couple of reasons. Um, the first is that, two-player zero-sum games are kind of like the canonical game. They're one of the few games that are extremely tractable. You can rewrite them as a linear program, and technically, then you acquire all the guarantees of linear programming solvers, all the complexity and so on. And second thing is they show up in a lot of places, right? So we can think of adversarial robustness as a two-player zero-sum game, GANs are a two-player zero-sum game, and then standard games that people play like poker or negotiation in like kind of military settings, like in diplomacy. And the last thing, and I think this is neat and maybe not universally known, is there are many games that can be recast as two-player zero-sum games. So things like mechanism design can be recast as a particular type of zero-sum game. And I've linked the paper that makes that connection at the bottom. So the first thing, if you're coming from an RL background, that you might want to do if you're thinking to like let's go solve poker, is to try taking single agent algorithms and applying them. So you might tackle IIGs with self-play RL. And the way the self-play RL works is you're going to take some copies of the policy. So here pi sub t is going to be the policy at iteration t. You'll make some copies of these and you'll play them against each other. That'll give you a bunch of rollouts. Those will go into some kind of training loop. So here, just train. And that's going to convert those rollouts into a new policy, pi sub t plus 1. And then you're going to repeat that process over and over again. And at the end, hopefully, you'll have a policy that is either low exploitability or close to a Nash equilibrium, right? So there's no way to exploit it. It doesn't necessarily win all the time, but it's unexploitable. And the problem is, and this is a GIF generated by Sam Sakota, naive self-play RL does not work in IIGs. So if we take a simple game like rock, paper, scissors, so here we're going to have, in a second, like what's called a probability simplex. Just to pause here for a second. So the corners represent the probability of play in action. So this corner here is 100% scissors, down here 100% paper, down here 100% rock. The center is playing each action with equal probability. And we're playing a perturbed version of rock, paper, scissors. So the Nash is slightly tilted towards playing rock and paper a little more than scissors. And if we start out at the center point and we run self-play RL, then what happens, unfortunately, is that rather than move to the equilibrium, we actually spiral away from it. This is like a known thing. And in the simple game, self-play RL cycles away from Nash instead of converging to it, which is not at all what we want. And so in response to this problem, what people often do is they take games from tabular settings, so from like matrix type games, where they have convergence guarantees, and then they take those matrix games, and from them they derive RL algorithms. So for example, there's a class of methods called like double oracle-based methods, and what RL algorithms that use this class, that are built on top of this class of methods kind of do, is you have some current set of policies, so here in this known policy circle, you play them against each other to create a like matrix of how each policy does against the other. Then use linear programming to solve for the equilibrium strategy over those policies. So if we have policy pi 1, pi 2 through pi n, we're going to play each policy with some probability given by this Nash solver. And then we're going to take that empirical distribution of how often we play each algorithm, and we're going to learn a best response against it. We're going to run RL against that distribution, and oftentimes it's going to expand the set of policies that we play. It's going to create a new policy pi, and that'll expand the set of known policies. And gradually, as this expands, it's going to probably converge to Nash. There are also a class of methods called fictitious play methods. And basically those replace, instead of playing against the empiricals, like the Nash over the previous set of policies, we play against the previous average strategy of all the policies seen so far. So the average strategy between pi 1 and pi t is what's going to be playing against that. It's what's going to be used to generate pi t plus 1. And that's going to also expand the set of strategies in a similar way. And then lastly, we have algorithms derived from counterfactual regret minimization. where counterfactual regression is kind of the like sort of best in class method for solving a lot of games. It's how superhuman poker bots are built. And there isn't a very obvious way to explain how it works in short. And there also isn't, sorry, I'm going to really quickly turn off my flux because it's late at night here. And as a consequence, okay, great. So do you all still see my screen?
No, not really.
Okay, you don't see my screen.
Yeah,
Amazing. Okay,
but you
that's
have to
unfortunate.
share your screen again.
Let me share my screen again, and then let's resume from here. Okay.
It looks
Um,
good now. Yeah.
better. And so you can derive kind of some kind of RL algorithm based on counterfactual regression. Now, these algorithms that are derived in this way have some pretty serious weaknesses. The first is both empirically and theoretically, they tend to have pretty slow convergence. They require a lot of samples. They may be expensive to run. Or if they don't, they may also come with complex importance sampling strategies. So you may have to do some like constant reweighting of how you sample. They also, rather than converge in the final iterate, they converge in the time average. And by that, what I mean is if you run the algorithm for big T iterations, the final policy at that big T iteration is not the Nash policy. The Nash policy will be the average of the policies seen so far. So you can't just even take the last policy. You have to kind of either keep all the policies around or have some way of continually representing the average strategy. And the last thing is they don't always have an RL analog. So it might not be straightforward to derive an RL algorithm from kind of these base like convergent algorithms. But in, I think, 2022, Sakota and D'Orazio et al. Put out a paper that suggested that perhaps the story about self-play not working could be wrong in some way. And they put together an algorithm called magnetic mirror descent. And magnetic mirror descent was sort of the first time that a self-play RL algorithm was SOTA in tabular settings. So it was competitive with counterfactual regret minimization, which is kind of a kind of the SOTA algorithm in those settings. And a cool thing about it is if you look at the functional form of magnetic mirror descent, the way it updates is if we have our pi teeth policy, then we update by looking at the Q values of pi t and kind of maximizing those, minus a KL term controlling the distance between the new policy pi and pi sub t, so control over the step size, plus an entropy bonus giving a bonus to randomness. And if you look at this and you squint at it, it looks a lot like a regularized policy gradient algorithm, right? It looks a lot like something like PPO, with the exception perhaps of the fact that this KL term is reversed, which is important in these settings. And so was very exciting because if we had self-play RL and we had self-play RL working, we would get all sorts of nice benefits. So we would have a single policy, right? We just have to keep whatever the teeth iteration is, and we can throw out everything before. It converges in the last iterate. So the final policy, if it's at equilibrium, is the Nash policy. And you could just take kind of like black box single agent RL algorithms from your favorite library and you could run them. So this would be very exciting if this was true. So what our work is first we build a bunch of new tools that allow us to exactly benchmark performance and compare self-play RL algorithms to kind of common algorithms that are used in this area. It is the largest ever comparison, we believe, of multi-agent RL algorithms for zero-sum games. And it is a first bit of evidence toward a unified algorithm that might work across a wide set of two-player zero-sum games. So what do we have to do to establish and compare algorithms in multi-agent RL and in two-player zero-sum games? And why is this hard? Well, if we think about what benchmarking in RL looks like and contrast it to benchmarking in multi-agent RL, when you want to benchmark an RL algorithm, you get some set of benchmarks. you run a bunch of your algorithms, and then you kind of compare the average score across those benchmarks. Or you might do something more complicated, but at the end of running an algorithm on a benchmark, you have a number. And in comparison, benchmarking in multi-agent RL looks more like this. It is a series of intricate steps with unclear outcomes at any given time. And it's worth thinking about why this is the case, right? So imagine that we wanted to build a poker bot, right? So we start with our poker game, we stick it into some algorithm, and out of that algorithm comes a policy pi. How do we know how good pi is, right? Because it's a multiplayer game, pi is defined relative to the performance of its other players. So the question becomes, who do we compare pi against? How do we know pi is any good without a reference? So measuring policy quality in zero-sum games is hard, and in games in general. There is another thing we could do, and that's to compute a quantity called exploitability. So basically what exploitability is, it's saying, if I were player one, how well could my worst case adversary do against me? And if I were player two, how well could my worst case adversary do against me? And take the average of those two things. And that's our average exploitability. And this is challenging because to compute each side of this equation requires solving an entire RL problem, right? I have my policy pi1, and now I need to find the exact best response against it, which requires solving an RL problem perfectly. And then on this side, I have to solve an entire RL problem again. And at no point do I know whether I've solved that RL problem correctly, right? So since I generally don't have any guarantees on RL, I don't know how far away I am from computing the true exploitability. I can run this process and I can get some number, but I don't know exactly whether it's the right number. So this is generally not tractable. And there's another approach that people can use. So instead of trying to compute exploitability in arbitrary games, we could use small tractable games. So this is a game called Kun Poker. It's a kind of short version of poker. You get some cards, you get a chance to check and raise, the other player gets a chance to check and raise, and then you fold and call. So it's like a couple steps. Each player gets at most 2 actions or so. And the nice thing about this is, for a small game like this, given a policy, you can compute exploitability exactly, right? Because the game is small, this computation exploitability is tractable. But the problem with the small games is they don't really tell you much about larger games, right? For these small games, it's not about generalization, right? You can enumerate the entire game tree, you can go to every cell, and you can tell exactly how well you're doing. But in large games, you basically never see a state twice, or it's very unlikely that you ever see a state twice. And so it becomes a lot more about generalization. And so the results in these small games aren't necessarily transferable to large games. So what we built is a tool called Expaspiel. It's kind of built atop of OpenSpiel games. And it contains 4 games, which are extremely large games, but for which we can solve exploitability exactly. So I'm not going to show you the games because they don't have a really nice visual depiction. But the important thing about these games that we're using in Expaspiel, and they're called Dark Hex 3, Abrupt Dark Hex 3, Phantom Tic-Tac-Toe, and Abrupt Phantom Tic-Tac-Toe, is that they have a lot of info states. And you can think of an info state as like, the number of equivalent states in the game. So it's like how many it's kind of the relevant measure of the size of a game for imperfect information games. So these games have millions of information states.
So that means kind of, in simple words, means different states, while the
Yes.
number of states have a lot of repetitions. Am I right?
Yeah. It's the number of meaningfully different states.
Okay, get
States
it.
that can be distinguished from each other. And so yeah, great question. So these games are very large, but by being clever, we can actually compute exploitability in them in 1 to 2 minutes. So you can do all your trading, and then at the end, you can run the code that we've written, and compute exploitability almost exactly, which will tell you like exactly how good or bad your policy is. And we do this through a mix of like multi-threading and efficient representations that allow us to compress the size of the matrices by using something called the sequence form representation. Okay, so we have these large games and we have the ability to compute exploitability in them. So now we're going to test a bunch of algorithms. So in each competitor class, like I'm saying competitor air quotes because we're not competing. We just we want to know true things about the world. We have one algorithm from each class. So we have NFSP for fictitious play, PSRO for these double oracle style methods. We have Escher for counterfactual regret minimization type methods. And then we have RNAD, which is much closer to the other methods we talked about. It's a regularized type algorithm. And is also the algorithm that was used to get human level Stratego or expert human level Stratego. And then as in our kind of policy gradient classes, we have PPO, we have the aforementioned magnetic mirror descent, and we have phasic policy gradient, PPG. So what we do is we run a fairly large hyperparameter sweep, about 5,600 runs in total, where we we do a preliminary sweep where we do like random search to pick, sorry, not random search. We randomize algorithms in some randomized hyperparameters in some carefully parameterized range for each of the algorithms. Then we take the 5 best hyperparameters from each of those runs and we run them for another 10 seeds to kind of get a careful result. And so to zoom in on the results from one of these games, here on the x-axis, we have each of the algorithm names. And on the y-axis, we have this exploitability. And what you want to do is you want to get a low value of exploitability. And in each algorithm, the first bar is the first set of hyperparameters run. And the second bar is the remaining 50 runs we did after we subselected hyperparameters. And what you can see in this plot is, there's pretty wide dispersal in the policy gradient algorithms at the beginning, but once we've picked good hyperparameters, they all get low exploitability. And lower exploitability than all of the other algorithms, with RNAD being a close competitor. And this pattern holds true across all of the games with a larger gap in some of them. And in particular, I want to here's another kind of view on the same thing where we've highlighted the policy gradient type algorithms in blue and the other algorithms in gray. And in red, we've drawn the exploitability of a policy that plays randomly. And what you can see is that some of the algorithms are actually kind of operating in the regime of playing almost at random in terms of how bad the resultant policies are. We can also look at the head-to-head performance of the algorithms when we play them against each other. So every box here is the performance playing one algorithm versus another. So here is PPO versus the actual equilibrium strategy, and it loses by 0.01, which is very close to equal performance. And so here, kind of in these columns, low numbers, you want to be as close to 0 as possible. Lower numbers are bad. And we can see across all the games that we kind of see a similar performance where the policy gradient algorithms are the best performers, both against all other algorithm classes and are not terribly far from Nash. So we have this kind of nice result that these policy gradient algorithms, these self-play RL algorithms, are quite performant, at least in these 4 games that we've looked at. And you might wonder why this could have been missed. And we conjecture a couple of reasons in the paper, but to call out a few. The first is that we tune the entropy regularization for these policy gradient algorithms. And in particular, we tuned it in a range that was much larger than is used in standard libraries. And we found that to be pretty important and helpful. The second thing is, maybe there's just not enough benchmarks, right? As I mentioned, in the absence of the ability to measure exploitability exactly for kind of large games, it's hard to rank algorithms. And so maybe just this lack of ability to rank in large games has been a bit of a bottleneck. And I want to end this section by talking about some cautions and limitations. So, we're making some evidence towards our hypothesis that regularized policy gradient algorithms are good here, but we haven't proven it. So some things to be suspicious of or to be cautious about. So first of all, for the other algorithms, we did our best to tune them. We gave them the exact same amount of computation time, sometimes a good more, but we still could be in the wrong hyperparameter regime, right? We took our hyperparameters from those other algorithms from standard implementations or the cleanest implementations we could find, but we may not have found the portion of hyperparameter space that works well for them. And so there's still a chance that things could reverse. Our games are homogeneous, so there's only sparse reward at the game end. There isn't any stochasticity in the game dynamics, and all the hidden information in the game is coming from actions. And then, the last thing I want to say is, we've open sourced all of this, so please, come test out this hypothesis about regularized policy gradient algorithms, and maybe we can learn something new. So to end this portion of the talk with some quick takeaways, we find that regularized policy gradient algorithms are outperforming every multi-agent specific algorithm that we test in these games. We build a new benchmark that lets us exactly measure algorithm performance at the end of training. And we make a step towards kind of a unified algorithm for multi-agent settings that's kind of easy to use. So now we know that in two-player zero-sum games, regularized policy gradient algorithms have a good chance of being pretty good. And the other thing that I'd like to talk to you about is what happens once you scale up regularized policy gradient algorithms. And show you that in some ways, multi-agent RL is ready to scale and create really exciting things with it. So I want to talk about this paper that we put on the archive maybe 2 or 3 weeks ago called Robust Autonomy Emerges from Self-Play. Every author here with a star is equal author, and our names are in alphabetical order. And this project was also kind of led by Stuart Bowers, Ozan Center, Philip Grambule, and Vladlen Colton. This is from our team at Apple. And what I'm going to talk about is how you can scale up regularized policy gradient algorithms to build an extremely robust multi-agent planner entirely from self-play. And so to kind of provide you with some context, we're going to be talking about autonomous driving here. And it's helpful to know what the autonomous driving stack looks like. So we have, first in the autonomous stack, we have perception. So like some LiDAR, some cameras, some radars fused together that tells us where everything in the scene is. Generally, that perception stack then goes to a prediction stack that, given the positions of the objects, kind of tells us how they're going to move. Given those predictions, we then feed them into a planning stack that decides where should we go next given those predictions and our perception. And so maybe it'll generate a bunch of trajectories, it'll cost them in some way, and then it'll pick out what it thinks is the best trajectory, and then control will help us follow that trajectory. And what we're going to present here is kind of the first fully human data free policy that we think looks like it could plausibly subsume this portion of the stack. And I've left out part of control because there's a little bit of control that we don't cover in here. And this policy is trained entirely using self-play at scale. And I'm going to provide you some evidence that it maybe looks like something you could just put in a car and put into the world, even though it is entirely trained without any data and is purely done in simulation. So this idea of using self-play RL to build policies that are like zero-shot compatible with humans that can be put into the roadway, there's often a common intuition that in some ways human data is absolutely necessary for this thing, because you could think about it as, imagine that we were to do self-play RL in a simulator with tons of cars, what do we think would fall out? And what a lot of people have is this intuition that what would fall out is this over-coordinated thing. Every agent knows the policy of every other agent because it's self-play. Because it's self-play. And as a result, agents kind of weave through each other without worrying because they know what's going to happen next, right? This car has decided to go, okay, that implies this. And following this logical chain down, all of a sudden you have all the cars smoothly interlocking. And obviously, this type of strategy would not be transferable to the roadway, right? This is not going to work with human beings. And I want to point out what I think is a subtlety, which is that if you are learning to drive in a diverse, multi-agent world full of uncertainty, that serves as a kind of regularization and a form of skill teaching that might be quite transferable. So imagine we play this goal-reaching game. We place a bunch of agents on a map, and we place goals all over the map, and we ask the agents to drive to the goals without colliding. The agents don't know about each other's goals, and they maybe don't know about like the risks, capabilities, and preferences of the other agents in the scene. And so to kind of think about like what you might learn in this game and how robustness might emerge from it, we think about this blue car, which wants to make a left turn and go towards its goal, which is represented by this green pin, somewhere further down the map. To make that left turn, we have this oncoming orange car. And this blue car, it doesn't know if this orange car is going to yield or if it's going to go straight. So it needs to learn to approach, keep some distance, maybe stutter, start and stop to try and figure out if try to induce that other car to slow down. And so this it can't just smoothly merge in front of it and know what's going to happen because that car might have a totally different risk profile and smash into it. Um, you know, similar things happen. Say you're driving here, you're the blue car, and you're trying to get your goal over here, and the car in front of you stops. Right now, you have to reason. Okay, it stopped. It's been stopped for a while. Okay, it's probably going to stay stopped. Maybe I can go around it. And you also need to be like very quick and ready to react to things that don't go according to your plans. Right. So this blue car is trying to go straight, but then the orange car cuts in towards it, this dashed line. And then as a result, we have to like aggressively, turn left to dodge the cut in. So we have to internalize a lot of uncertainty. We have to reason about the unknown goals of other agents, their unknown capabilities, and we also have to be like really robust and ready to react. We want to keep safe buffer distances from other agents. We want to be ready to get out of their way quickly if we need to. So we can learn a lot of things from these goal-reaching games, and a lot of these skills are going to be transferable to other agents than the ones we've trained with. There's going to be some possible generalization that comes out of this. So what we built is a simulator that we call GigaFlow. GigaFlow is an entirely PyTorch-based simulator, but because it's based on PyTorch, the whole simulator is batched. On each GPU, we're going to place 4,800 copies of these different maps from Carla, which is an autonomous driving simulator. And these maps are quite big. Some of them are, kilometers in any direction. And on each of those maps, we're going to place up to 150 agents. And then we're just going to throw goals all over the map. And agents are going to drive around, get to their goal. When they get to their goal, they get a new goal and they're going to keep driving. And they want to do that without colliding. They collide, they come to a stop, and they're frozen for the rest of the episode. And as the agents get more capable, we can just keep running the simulator forever, so on. Within any segment, we have in GigaFlow, we're gonna have a single policy for all agents. It's not centralized, it's completely decentralized, but every agent is a copy of the same policy. So they share weights, but what they do not share is conditioning. So they each receive their own observations, like the road, the lane points, the stop lines, and their own state, how big they are, how fast they're going. They receive a view of the scene around them, but then they also receive conditioning and goals. So they have their own unique goal, and then I'll talk about this a little more, they have a little bit of conditioning that makes each of them act in a diverse fashion. And I'll talk about that in a second. So we scale this up massively. We train for about 10,000 years of driving experience in the simulator. So 8 GPUs for 10 days generates about that much driving experience with millions of simulated drivers operating in the simulator at any time. And we generate about 1.6 billion kilometers of simulated driving. In total, based on like AWS cloud costs, this is about $7,000 to train. It's probably lower in reality, but if you just pay on-prem prices, this is about how much it costs, which I think is very little for how robust this policy is going to be. And if you want to just roll it out, it's about $5 to generate about 1 million kilometers of driving. And if we were to plot 1.6 billion kilometers on this plot down here, it's about the distance between the sun and Saturn. Which is, a good deal larger than the amount of driving in any available human data set. So as I mentioned, these agents have some amount of diversity. And you might ask where that diversity comes from. It comes from a couple places. The first is it comes from reward conditioning. So we have a couple of reward terms, and each of those reward terms is weighted by some weight vector. And we provide the weights of that vector to the agents. And so the agents know how much each reward component is weighting. And how much it's weighted for them. And they're very responsive to this. So for example, this term here is called center bias, and it represents how much the agent wants to stay in the center of its lane. And if we put it to 0, it doesn't care what lane it's in. It'll go all over the place. And if we make it high, it'll try to stay in the center of its lane. And, we have similar terms like this for comfort. So driving jerkily, staying aligned with the heading of your lane, um, how urgently you want to get to your goal, things like that. And we also have a lot of diversity through, I'm going to skip this slide, through size conditioning. So, oh, sorry, actually, let me go back. Through goal conditioning. So agents care about their goal. And so over here on the top, we have 3 different goals, and the agent will take a totally different trajectory depending on which goal it needs to go to. And then they also have diverse sizes. So we have agents representing cars, cyclists, pedestrians, and based on their size, they have totally different behaviors. So over here, we have a goal on the bottom left-hand corner, and we have 3 cars, 3 visualizations of the car. If we're the narrow green car, we know we can squeeze through this obstacle, and we'll just drive right through. If we're the blue car, we know we can't squeeze through the obstacle, and we're kind of big. So we're going to our cars will execute a 3-point turn and go around. And if we're the small rectangle, we also can't squeeze through the obstacle, but we are much more maneuverable, and we're going to just do a quick U-turn and go around. So there are a lot of diversity coming from the size conditioning, from the reward conditioning, from the goal conditioning, and things like that. A cool thing about GigaFlow policies is that they're almost near perfect on all the benchmarks we've tested them on, despite the fact that they have never seen those benchmarks and they have never seen any human data. So let's go through 3 benchmarks, the 3 benchmarks that we test them on. The first is this Carla benchmark over here on the top left. It consists of like 5 to 20-minute drives with hand-designed human actors. So it's driving around in a world with agents that have been hand-scripted. It has never seen those agents. And despite that, it outperforms the prior Carla-specific state-of-the-art by a lot. It's a little hard to understand what this number is, but like Carla has a driving score that you need to optimize. It's not actually clear that you can get 100. And when we watch the videos of any place where we were dinged for points, we think that it's mostly the benchmark that's at issue here. We also look at benchmarks that contain human data. So this is NewPlan, which consists of drives in Boston, Vegas, and Singapore, and a couple other cities. So this actually contains human replays. Like all the agents here are following trajectories that were driven by humans, and we have to drive amongst them. And despite, again, never having seen any human data, we outperform NewPlan's specific state of the art. And in particular, in NewPlan, there are a total of 15 failures in the entire benchmark that we observe. Of those, 9 are caused by a car teleporting on top of us, so nothing we can do about it. 4 are caused by a pedestrian ramming into the side of our car while we're at stop traffic. So again, literally nothing you can do about it. It's kind of more of a benchmark issue than anything else. And then 2 that are maybe contestable. So we're really pushing the limit of benchmark performance here, and additionally in Waymax, which is another driving simulator that mostly consists of data from San Francisco and Phoenix, I believe. So we are kind of pushing the bounds of performance on synthetic benchmarks and on benchmarks containing human data, despite the fact that we've never trained on those benchmarks, never trained on human data. The other cool thing is that if you take GigaFlow policies and you place them into settings that are extremely out of distribution, they figure out how to solve them by the end of training. So here we have a big road and there's a bunch of cars piled up back here. And there's, in red here, we have an obstacle. You can't drive through that. The beginning of training, they kind of fail to model through. They like smash into each other. They smash into the obstacle. But by 10 to the 11 steps of training, they're all able to negotiate to get around the obstacle. We don't have videos. They'll be released in mid-March, probably, we hope. But you'll see, when we release this, you'll see the cars like smoothly negotiate who gets to go. Like cars will back up to resolve a bottleneck. They'll kind of jiggle around to kind of figure out who should be going. And by the end, there are 0 collisions in any rollout, and they're all able to smoothly get through that bottleneck. We also see evidence of long horizon decision-making in our policies. So here we have our vehicle. It wants to get to this goal. And over here, there's a little obstruction about 156 meters away. Now, it's 156 meters away, but it's many, many seconds away. So it's many time steps away. So if you are using some kind of like sampling-based method that doesn't have abstractions built into it, this is too far for like a method to reason. But our value function says getting near, we see that our value function knows that getting near that obstacle is bad, even though it's extremely far away. And as a result, our policy knows this too. And it like goes here, and instead of trying to drive near the obstacle and turning around, it just reroutes itself and drives the car. So it does really long horizon routing behavior, which is kind of cool and new, and I'm not sure has been seen before. And the last thing I want to say, for an RL policy, for an entirely end-to-end policy, I mean post-perception, but end-to-end, it is extraordinarily robust. So in self-play, after about 80 hours of training, it goes a million kilometers between crashes. Humans crash somewhere between every 20,000 and 100,000 miles or kilometers. Forget if it's miles or kilometers. Um, so when I say human level, I mean that in self-play, we are, extraordinarily robust, despite the fact that we are entirely end to end. And I'm not sure this level of robustness has been seen in an RL policy before. And the last thing I want to point out is that this planning policy is tiny. It is a couple layers of MLPs with a little bit of equivariance, permutation equivariance placed at the front. And in total, it is about 3 million parameters. So despite all this robustness, this is just 3 million parameters doing all this driving, which is nice because you can inference it really, really fast. So some quick takeaways before I go forwards. I want to put forward this idea that driving or behaving in an extremely uncertain or diverse world is a strong constraint on the rational multi-agent behaviors that you might have. So if you just run self-play and you make your world diverse and uncertain enough, the thing that emerges has to have some amount of robustness to out of distribution actors, because you can't like overfit to the actors that you play with too much. We put forward the first simulated planner that appears to zero-shot ACE benchmarks. And I want to throw out one more idea, which is this idea of like large-scale self-play as pre-training, right? So we can do this like large-scale self-play. And at the end, we learn all these sort of capabilities that can probably be repurposed for other tasks. So maybe we're not perfect for another agent that we want to test with, but we're pretty good. And then we can just fine-tune on top of it a little bit to get something nice. A couple limitations to kind of end off this talk. The Gigaflow driver, while it is robust, is not particularly human-like. Nothing about this procedure induces human likeness. It doesn't have the same cognitive biases humans have. It doesn't have to, look left or look right to pay attention. It doesn't have attentional limitations. And so, this gives you something, but it doesn't, human likeness is not like the emergent property here. We observe a lot of benchmark saturation. So it's really hard for us to tell if there are remaining failures in our policy just by looking at the benchmarks. So, it could be worse than it seems, and the benchmarks are just not strong enough to tell us. And this is all in simulation. So we haven't put it in a car yet. My lab is hopeful that we will get a chance to do this in the next couple of years, but we haven't done that yet. And the last thing I want to say is like, the thing that emerges here is robustness, which if you're trying to build cooperative artificial agents, it's not exactly what you want. It's not the same thing as effective teaming. Yeah. So I want to kind of end with a couple of next steps that my lab is pursuing. In particular, work spearheaded by Daphne Cornelise, Kevin Joseph, Arif Pandya, Sam Kazimkhani, Joseph Suarez, and Brennan Shacklet. We've been building a simulator called GPU Drive. And unlike Gigaflow, GPU Drive goes from C++ to CUDA. So you write C++ code, you get a CUDA simulator out. And it's built upon this Madrona framework that lets us do this. It's a really cool framework. Highly recommend checking it out. And the nice thing about that is that instead of having to solve complicated tensor puzzles to batch things, you just write C++ code and the compiler like batches it for you. We are able in GPU Drive to train policies that are collision-free in 99% of rollouts. That's not yet at the level of Gigaflow policies, but we're getting there, and we're doing it fairly sample efficiently. So this happens quite quickly. And the last thing is, we want to tackle this unresolved issue of like human likeness. So we've been incorporating human data and using it as a regularizer to try to build policies that are both capable, never crash, but also kind of look quite like humans do. And here I've linked two papers that cover the topic, one of which is out of iClear, and one of which was published in the Reinforcement Learning Conference in 2024. So I want to end with some acknowledgements. All these folks contributed to this work. It wouldn't be possible without them. I am just a mouthpiece for their great work. And yeah, and with that, take any questions that you all have. And so thank you very much for your time.
Yeah, thank you so much, Eugene. It's a wonderful talk. And there is one question in the Q&A tab. If you can click on it, you can see the question.
I might have to unshare to see it, but
Yeah, yeah,
I'll go
sure.
back to that. So multi-agent RL is often seen as computationally expensive. How does your approach reduce the computational burden while maintaining or even improving performance? Could this make reinforcement learning more accessible for real-time applications? So I don't know that we've necessarily solved the computationally expensive part. One piece of this is a great question. One piece of this is that like we're writing really fast simulators. So even though it's computationally expensive, right, the simulator kind of helps out a lot. Um, in Gigaflow, we can train a pretty strong policy in like a day or two on a small number of GPUs. And in GPU drive, on a single GPU, we can train a pretty good policy in a day, and that number keeps going down. So that's expensive, but it's not insanely expensive. Um, the other thing is that these policy gradient algorithms, they are computationally expensive, but they're not necessarily wall clock expensive. So they run pretty fast, even though they compute a huge number of samples, right? Because you can like parallelize them very nicely. So I guess that's a partial answer to your question. But I think that like what I hope to get across the Gigaflow is that these things and GPU drive is that these things are accessible. Like the techniques are pretty stable. You can just go out and run PPO, and things mostly work pretty well. Um, and it's not totally out of scope for a lot of people to try. Is that it? Yeah. Thanks. Um,
And Jin Yu has a question. He raised his hand, so I will ask him to unmute himself.
Hi, bro. Can you hear me?
yeah, I can hear you.
Yeah, a wonderful talk, bro. It's so interesting. So, I mean, to start off, I'm curious about what is the novelty of the recent work. So, is it that um, robust autonomy emerges from self-play when we choose the correct task and we um correctly randomize the task? Because I guess this seems quite obvious like now that this paper is out, but in the past was this like not um something that was not known or like how did
Yeah.
people do this in the past? Yeah.
So it's always tough to conjecture. It's a great question. It's tough to conjecture about what people believe. Maybe Damo could say, but can comment. But if he feels otherwise, but sorry, I didn't mean to put you in the spot like that. But I think that if you had said like, can you just run self-play, do all this synthetic data, and get something that like looks like a capable driver for holdout policies, I think like a lot of people would have the intuition that that's not the case, because like human driving, it has got a lot of conventions. There's particular ways you have to behave, and so on and so forth. Um, and I think the other piece that I think is surprising is like the amount of robustness, right? So people do not think of RL as this like thing that can generate extremely precise performance, right? It gives you something that's like really good, really fast, but it's not like on par with like wrapping, having a complicated control architecture and wrapping it in a safety layer and then doing all this sorts of stuff. But this is just like an end-to-end policy that is insanely robust, at least in self-play. So like it kind of points to there not necessarily being a bottleneck in like pure RL scaling. Um, Yeah. So maybe I think those two things are a little non-obvious, and even though we've shown them in this example, I think you could say that they might not generalize to other examples. Maybe this is a one-off case and it just works here. I think these ideas are actually applicable in a lot of domains, and particularly the thing about if you just scale up RL, there's really no wall. Like it just keeps going. You can take the same kind of scaling ideas that were working in supervised learning and apply to RL and not stress out. Um,
Yeah, bro.
yeah.
That's a follow-up question.
Mhm.
Yeah, so I think Tesla and Comma and like other companies, the
Mhm.
reason why they use human data is also because of the long tail distribution
Yeah.
of very random things that might happen in the real world, right? I think
Yeah.
Tesla gave like some example of a truck having a picture of a ladder at the back and like its
Yeah.
agent didn't know what to do. So do you see this kind of random things happening as something that's solvable with simulating other random but precise or like clever goals that you construct in the simulator? Do you think it's
Yeah.
solvable in this regime?
So I want to talk, this is a great question. I want to break it up into different types of long tail things, right? So the example you gave is a perceptual failure, right? We're not in perception, we're post perception, right? And so we're not able to like deal with perceptual failures. Um, I kind of think that we'll make a lot of progress on perceptual failures just through synthetic data and simulated data. All these simulators are getting really good. You can build all sorts of weird photorealistic looking scenarios into a simulator. We're not doing that, but I think it's possible. But there's also like planning level failures, right? So something really weird happening. And from the planning perspective, the set of like failures that can happen are a lot more constrained, but still hard to construct and rare to see. You know, how often do you see a car driving down the wrong lane of the road going at high speed? That happens in our simulator all the time, like constantly. Um, and there's just fewer long tail planning events that can occur, but you still have to construct them somehow, and you don't see them in the real world very often. So I do think that for like planning level failures, I think this looks pretty promising to me.
Okay, I ask one more question. So
Yeah.
I think naturally it's I'm wondering why don't the work use planning or any kind of differentiable, because it's a differentiable simulator, right? So
Mm-hmm.
you can essentially train it very efficiently using backprop through the simulator, and then you can. But then it seems like you guys are just using a very simple PPO algorithm. Is
Yep.
there a reason why you don't use differentiable simulation? And also, why don't you use the simulator during inference for planning or for prediction?
Okay, so a couple things. I'm going to do the second half later. First, so we could use the simulator during planning, right? So we could do test time search. Totally reasonable, totally a thing you could do, probably a thing you should do, would make our results better. I played around with it. We didn't have time to get it into this paper. Um, from the question of why we don't use like differentiable planners, I think you want to learn these like complex long horizon value functions. They're kind of straightforward to learn through in model free RL. But there's not a reason you could try to do this with differentiable planning. People are welcome to try. This is just like a thing we did that worked. Um, I think it would also be a lot of work to try to scale differentiable planning in this way and see if you could kind of recreate these results. Kind of an open question. You know, I think someone should try.
Thank you, Prof.
Yeah,
Yeah, great question.
maybe 2 or 3 questions. Sorry for that. Okay,
Yeah,
so
go,
for
go.
one is this replaying you are doing with GigaFlow. It's a bit, I mean, to many people, it's probably similar to building say something like a foundation model for self-driving. And the question will be, what do you think is a major gap between what you have now and what can be applied in many different companies, different countries, and the foundation model for self-driving?
So I think when you think of something as a foundation model, right, what does that mean? It means it can either zero shot, where it can do tasks, or it can be fine tuned. We
Yeah.
have evidence of zero shot, right?
Okay.
Like we are testing in benchmarks we've never seen.
Mhm.
Um, and I think maybe the missing thing is to show that in the real world.
Yeah.
We don't have evidence yet of the fine tune. I actually think that you could fine tune this pretty well, that it would be a base, but it's not something we've done yet. But I think that if we showed evidence of zero shot and fine tuning, I would say like that looks like a foundation model.
Yeah, so my major question would be, say, can you have a certain, a kind of fixed component in your simulator or your PPO policy, right? For example, you have truck, car, you may have bike, but you don't have the thing called tuk-tuk, which are the small vehicles.
Yeah.
Yeah, so those things, if you use it in Southeast Asia here and then in other places, so for foundation model, it's like to be adapt to those new tokens or new representations as well, right?
Yeah, so it's a great question. So we have a finite number of things. We don't have a distinct notion of pedestrian, cyclist, or driver. We just have boxes of a certain size that move in
Oh,
a
I see.
particular way, right? So they're not new tokens. And in some sense, like the challenge is mapping the world to this representational space. But if you map a tuk-tuk down to like a box of a certain size that can move in a very surprising way, that's
Okay.
kind of in our simulator. Um,
Oh, I see. I see.
so like you can map it down to that. And we have weird looking boxes that will move in very surprising ways. And I think so like if you can make that mapping down into the representation, I think it's kind of there already.
I see. I see.
And
Okay.
I think
Well,
if you probably went to the new plan benchmark, since it drives in Singapore, I'm guessing some of that is in there actually.
Oh, I see. I see. I don't know yet. Haven't seen any self-driving cars here in Singapore yet.
Yeah,
Yeah.
yeah,
One more question is you mentioned the RL policy behave different from human, but
yeah.
in reality, human have to follow some traffic rules by law, and the laws vary among different countries. So how difficult is it to integrate those human written rules into those RL regions, like follow certain kind of
It's a great question. So some of the rules are already in there. So
okay,
we do look like a human policy with respect to rule following. And this
yeah.
is sort of a problem that self-driving car companies have had to solve. You have to write down the rules as some kind of like cost function, right? At some point. And so people can do this. Oftentimes, a lot of the problem isn't even in writing down the rules. It's like sometimes you have to break the rules.
Oh,
You know, so you, if you, I mean, maybe if you, there are situations you can get into where you're like in stop traffic for like 2 hours and the only way out is to for the rules to break down and everybody start doing like weird illegal weaves around each other.
okay.
Um, but I don't think this is like a huge bottleneck. We are actually following most of the rules here. We didn't encode every rule in the rule book just because like it didn't seem like necessary to prove a point. But you know, it's a thing you can do.
Okay.
Great question though. Yeah.
Well, one last question before we turn back to Jinyu again. So, in the first part of your talk, you talk about zero-sum games. I'm curious because nowadays a lot of people talking about AI safety. So you can
Yeah.
have one agent be the safety guard, another one is the one doing a tank and the safety stuff.
Yep.
So, do you think that will be a similar type of application? And you also show this divergent reverse attractor. And do you
Yeah.
think around your Nash equilibrium. So what's the nature of that happening? Would that happen to the AI safety guard? Do you think? Yeah.
Um, so I think a lot of the like this is happening in that case. These things happen because of imperfect information or because of simultaneous moves.
Okay.
If you have full information and alternating moves, this is less of an issue. And then like you can do like MCTS like things and things like that. So it really depends if you're in that setting. But if you're doing like, you know, AI safety in this kind of like imperfect information setting, then all this stuff happens. And I think all of these algorithms start to matter again.
I
Um,
see.
yeah.
Okay. Yeah. Thank you so much.
Yeah.
Jinyu,
Great questions.
one more. Do you have one more question? Yeah. Jinyu, you can unmute yourself.
Oh yeah, so Rob, I think one big question I have is so Tesla and Comma recently moved to an end-to-end stack, right? So I think previously they used there's a stack similar to the one you showed, but then recently they went end-to-end. So yeah, so like how do I think about it from as someone who is also researching kind of in this area?
Yeah.
What do you think about it? I'm quite curious as well.
So there's a few things. The first thing is I'll believe it's end to end when they put out their code and they put out their architecture and like show me that it's actually end to end.
See,
I bet there is a safety layer in there somewhere. I could be wrong, but I can't know, right? I don't work there and they, you know, they're not operating in the open source community. So what do we know, right? It's just words. Um, I would love to see it though. Please, I hope so they do that one day. The second thing is like I think this imitation learning thing is going to go really far, like really far, surprisingly far, farther than you would expect. Um, but I think it's going to cap out at some point. Because like the scaling of that last little bit of robustness, the thing that you really need before you can like actually put it in the world and like feel like totally confident and not have a human supervisor there. I think that that is kind of where you're going to start finding that, you know, more and more imitation learning data is like barely cranking away at those nines. Um, so like if I'm gonna bet on where imitation learning caps out, it's there. And I think like you kind of see this in like think about like ChatGPT. ChatGPT is trained on so much data, and it still like makes mistakes too often. It's you know it is an imitation learning policy.
Yeah.
So I am skeptical that this gets you all the way. And I think at some point these companies are going to need to start doing RL or something that looks a lot like RL, even if they get surprisingly far with imitation
I see. That's very interesting. Just one last question about the randomized reward conditioning.
learning.
So, it seems like it's a very interesting approach, and it seems like it could like one way that the agent is generalizing so well is because of this, right? And
Mm-hmm.
do you see that this can be a way to code in ethics as well. So like in the example that you gave just now, right? Like where the traffic light broke down and then people had to break rules. So it seems like there's a change in this reward weighting when certain things happen, right? So do you see that this can be a way to map in this long tail distribution and also handle ethics as well?
Yeah, that's a great question. I think so. The first thing I want to say is like, if you look at the paper, we have a bunch of oblations in the end. We were like insanely thorough, and you can see how much the reward conditioning contributed to the resultant robustness of our policies. It's a bit, but it's not like the most major thing. But I do think the thing that is surprising is how controllable these policies are. It's like you can fit so many sub policies into this one tiny little neural network, right? And so you get all this like flexible conditioned behavior. And so I do think there's like you could stick more reward terms in there, and you could really flexibly recondition its behavior to behave differently when a certain scenario happens. So yeah, I think the policy that you get out of it is surprisingly controllable. And maybe that's also, to answer your question, maybe a little surprising that you can kind of fit so many sub policies into this one little neural network, or get this type of conditioning. So yeah, I think what you're saying could work. Yeah.
Thank you so much, Prof.
Great question.
Other question? We're already like 7 minutes past 11. If there are no other question, thank you so much, Eugene. It's a wonderful talk.
Thank you all so much for your time. It was a real pleasure.
Thank you so much for
Thanks for the great questions.
so late. Okay, thank you. Have a good night.